Today's webinar speaker is Raj Moulik from Princeton University. Raj is a planetary scale geophysicist who works on a variety of phenomena that shape our planet. Specifically, he employs and extends the tools of seismology to probe the Earth's deep interior. These novel methodologies also lead to a better understanding of devastating earthquakes. Raj received his PhD from Lamont Doherty Earth Observatory and went on to a postdoc at the University of Maryland, where he worked with a team to construct a 3D reference Earth model. He's here today to talk more about this work, and in particular tell us more about AVNI, the Analysis and Visualization Toolkit for Planetary Inferences. So we have a large audience here today, and I'm hoping you are intrigued as I am in how we can use this tool in our research, and hopefully have lots of questions for him. So with that, the screen is yours, Raj.
Thank you, Lauren, and thank you all for attending this webinar. Today, I'll discuss progress towards creating reference Earth models and the underlying reference datasets. I will also discuss some published and unpublished scientific results that leverage AVNI, which is a software environment that stands for Analysis and Visualization Toolkit for Planetary Inferences. The software components of this work are the result of an excellent team of code maintainers and web developers listed here. And the scientific results are due to a large collaborative effort to create the next generation reference Earth model. The aim of this particular talk is to discuss the motivation and setup of AVNI and to get feedback from the community before its release. As we discuss various components, what I'm looking for is input on how we can better facilitate your research. As geoscientists, we are motivated by the need to answer several outstanding and fundamental geological questions. For example, how well does the transition zone modulate the ultimate fate of descending slabs? Which is also related to the question, what is the style of convection in the mantle? The other question is regarding the presence and the characteristics of large-scale thermochemical heterogeneities in the mantle. And what does that mean for the stability of these long wavelength superplumes that arise from the core mantle boundary? In the shallower parts of the mantle, an outstanding question is regarding the distribution of large-scale anisotropic variations, especially at the mid-ocean ridges and beneath oceanic plates. And anisotropy can also be used to infer mantle flow and rheology. So these are all questions that motivate us. A way to tackle outstanding geological questions is to reframe them in terms of geophysical questions. Answering all of these questions requires descriptions of the Earth's interior and assessing the extent of structural complexity. Now, structural complexity can be either in terms of geometric parameterization, in other words, a core scale parameterization versus a finer scale parameterization, or a combination thereof. It can also be in terms of the parameterization of seismic models in terms of density, anisotropy, or attenuation, and the inferred thermodynamic parameters, such as pressure, temperature, and grain size. For the question on chemical heterogeneity can be explored by looking at scaling relationships between isotropic shear wave velocity versus isotropic P wave velocities and densities. The question on the style of convection is related to the features of heterogeneity in the mantle. The plot here shows the correlations between pairs of depths with red as high correlations. This shows that the lower mantle has contiguity in depth of long wavelength features. That this contiguity is reduced in the upper mantle, where features don't extend as deep in a contiguous fashion. there is an abrupt change at around 650 kilometers depth. Similarly, the strongest power of heterogeneity is also in the upper mantle, especially at the longest wavelengths shown in red here, and also in the lowermost mantle. All geophysical questions, in turn, are applications where seismological data and models come in handy. For example, the evaluation of seismic parameters from archived models can be used to populate and create a finite element mesh, and also explore radial profiles with depth. Other applications, such as locating explosions and earthquake early warning, require rapid predictions of data. These often involve predicting a derived quantity, such as an arrival time or an amplitude of a seismic phase, rather than the full waveform. Geodynamic simulations report variations in structural properties with time based on prescribed initial conditions and mineralogical parameters. Here is an example that shows a rifted margin and the developing crustal structure coupled with a surface evolution model. Seismology provides constraints that can be used to validate and even inform the parameters that are used in these simulations. Today's focus is all about tools and ways to bring all of these things together. I will discuss the 4 prongs and underlying tenets of the Reference Earth Model project. I will first introduce the concepts of the AVNI software environment. I will then discuss how AVNI is set up for various data, theory, and model applications, which have led to some new scientific insights. At the end, I'll come back to the community prong and discuss how you can be an important stakeholder in this effort. Let's start with the community prong, where we want to maximize utility for geoscientists. All geoscience applications require flexible computational workflows. These typically involve querying data or models in order to make inferences. This process can be aided by visualization of various Earth models, comparing them against each other, and predicting data. Predictions can also involve uncertainty about our inferences and the evolution of the model itself as more observations emerge from new seismic stations and with time, like in geodynamic simulations. All scientific questions in the rest of this talk are tackled using a combination of these workflow elements. AVNI is a software environment powered by Python that facilitates these computational workflows. The overall setup was created for what is inevitably going to be a web-based future, a shared infrastructure where users will no longer have to store data, compile and run intensive codes on their own machines. The backend databases are hosted on servers and are accessible to you, the client, through various front-end options. Application programming interfaces, or APIs, authenticate and schedule access to these backend resources using the latest standards in NSF-guided cybersecurity protocols. The components for AVNI can be categorized into private, public, backend, and front-end categories. All users have access to a public space shown in a dashed box here, which includes a website for registration and a pure Python package that can be installed on your own system. These can be imported on your machine through the command line or through Jupyter Notebooks. The green boxes here are ways for you to interact with the AVNI resources. The private space on the backend servers, shown in a solid box, includes a more comprehensive code repository with bindings to legacy codes in Fortran and C, Backend servers also store static files and databases. AVNI provides interfaces to query subsets of these data and ask for predictions through any of these front-end options. This involves first authenticating the user, allocating memory, and creating temporary files whenever necessary. Let's see some potential use cases of AVNI. Here are examples of client-facing front ends built with AVNI. The first is a web-based applet accessible through a client's web browser. So this particular example shows how to query and compare arrivals of surface waves measured by various research groups. These applets aid reconciliation of data made by different techniques. This particular video shows comparisons of measurements and how it can be filtered based on wave type, region, or association path. Note that metadata are displayed interactively on the plots, and selections change the output of other plots. Here are two examples that, on your right are two examples that utilize the model formats in AVNI to evaluate various model parameters, which can then be accessed using either command line or Jupyter notebooks or through a GUI that you might build. On the visualization part of the workflow, a key aspect is its interactive nature. This is accommodated for the data web applets through in-memory data frames and file system storage. The result is a seamless experience on the web browser where user selects subsets of data, identifies outliers, assesses uncertainty, and creates output like dispersion curves, travel time comparisons, and differences between arrivals of different surface waves. Another set of interactive visualizations involve that of Earth models. The metadata for Earth models includes the reference models used in the model construction and the scaling between VS and density and other parameters. This metadata is used to populate mesh elements and grid values using the AVNI codes, which can then be queried through the command line or through a web-based setup. Now let us look at the data prong of this work that has been built using AVNI codes. The underlying tenet here is that we want to create that different techniques actually see the same Earth, albeit through different lenses, and we therefore should be able to get a consistent set of measurements that would constitute the reference data set. The computational challenge with data is that there has been a rapid explosion of various data types. Since 2000, there has been a 6-fold increase in the number of stations and a related 3-fold increase in the number of earthquakes detected by the global CMT catalog. However, the heterogeneous distribution of stations is readily apparent, with more coverage in the Northern Hemisphere. Now, there are several legacy and emerging techniques to measure seismic data. Here's an example of a seismogram from Charter Towers, Australia, from the 2004 magnitude 9.1 Sumatra earthquake. One way to analyze this kind of data is to download the whole waveform, process them, and try to fit this with Earth models. You could do the same thing in the frequency domain to create spectra that can be modeled with Earth models. However, I believe we should be harnessing the legacy wisdom on modeling derivative measurements of body waves between 1 to 30 seconds, surface waves between 20 and 300 seconds, and nominal modes between 250 to 3,300 seconds. These derivative measurements can include values from time domain seismograms, such as dispersion curves and arrival times. or measurements from frequency domain spectra, such as fitting functions or singlet eigenfrequencies. It has been our experience over the last several decades that fitting the full waveform and spectra in global seismic imaging requires, number one, a good starting model, and two, knowledge of credible wave packets, both of which can be informed by existing derived data. We store the metadata of these derived data in modern scalable formats. I will discuss the reference seismic data format, especially in case of the dispersion of surface waves, since this has been published in a recent study. These datasets are both provided both in HDF5 and ASCII formats. The header of the data contains values such as citation or the different reference models and other aspects that are common to all measurements. And each of the rows correspond to different different values of different paths that can tether the measurement to the relevant wave packet in the seismogram. The AVNI code base can convert between both ASCII and HDF5 formats. Once various methodological biases have been accounted for, it can be shown that a substantial amount of the signal in the data from various techniques can be reconciled. Here's an example of measurements from two different techniques. So these are arrival times of 100-second fundamental mode Rayleigh wave from two techniques, multimode dispersion on the y-axis and mode branch stripping on the x-axis. Each of these dots is a path along the surface of the Earth. You would note that both of these techniques are highly consistent, except for some outliers, which are usually from issues like cycle skipping and polarity reversal in the instruments. This comparison is one of the many comparisons and analysis that has been done for surface waves from around 44,000 earthquakes recorded in 12,000 stations by 8 groups across the world. Now, those were the measurements. Let's look at what inferences can we make regarding Earth structure. Here is an inverted map of log waves at 100 seconds. So this is the type of wave which is sensitive to structure in roughly the top 150 kilometers of the crust and the mantle. All of these lower subplots are measurements of isotropic phase velocity, where fast is in blue and slow is in red. You can see clear tectonic signatures from the upper mantle of mid-ocean ridges and cratons. The summary data set, which represents the consistent measurements across all of these different groups, shows that the features are consistent across different techniques and represent the tectonic signal from the upper crust and upper mantle. Another way to look at this comparison is to quantify consistency by taking pairs of these maps and looking at correlations. Here, the lighter colors, light yellow, are correlations between pairs of catalogs where the correlation is above 0.8. Here, you can see that for structure at degree 15 to 18 and below, so very long wavelength features, it doesn't really matter what technique is used to make the measurement. They all provide similar structure. The same can be said of the power of these maps. You get similar values of power irrespective of the technique that is used in the measurement. Another aspect of model complexity is to look at features, parameters like azimuthal anisotropy. Here, the bars represent the fast axis of surface wave propagation. Two things emerge. All of these techniques show a consistent fast axis in the Pacific Basin. The blue colors here represent magnitudes of anisotropy. So the strongest anisotropy is in the Pacific Ocean Basin. And overall, oceanic basins have stronger anisotropy compared to continental structure. Now, I just discussed aspects about surface waves, but the similar analysis can be done for body waves, where we have previously compared measurements of different P waves, differential P waves and S waves, and found similar level of consistency across measurements. These have all been updated in a separate manuscript. And we have also done similar analysis for normal modes, where recent measurements provide very higher precision values of frequencies of different modes as a function. Each of these x-axis is a different normal mode that represents a unique vibration in the Earth. And this is for Rayleigh wave equivalent spheroidal fundamental modes. You can also look at the splitting function, which is equivalent to a phase velocity map, but for mode eigenfrequencies. And both individual modes like 0s2 and cross-coupled modes are highly consistent between different techniques. Now, what AVNI can do is provide rapid predictions of data, especially with regards to these reference data sets. So for example, here is a fast calculation example of fast calculation of a travel time from PREM in this case. And this is done just with 3 lines of code, and it queries the API on the back, which then calls the backend codes and gives you the arrival time of any particular phase. This is done using anisotropic 1D anisotropic ray tracing. We have not yet implemented 3D anisotropic ray tracing, which is also something that is missing in the community, and it is being worked on right now. The second prong of this project is to apply appropriate theory so that we can take all of these reference data sets along with AVNI and leverage the complementary sensitivities in these data. So this is what I call as full spectrum tomography, where we have different types of data, such as astronomical geodetic data. This may include the gravity field or the geoid, mass and moment of inertia of the Earth, surface waves, and surface waves span this frequency range, 25 to 300 seconds. Usually this can be done with either dispersion curves or with phase velocities of Rayleigh and log waves. Waveforms can be modeled, wave packets in the waveforms can be modeled using various theoretical frameworks. Body waves, especially of the arrival times of body waves and time distance curves. So arrival curves can be included. And there are various aspects of normal modes that can also be included in this setup, which includes both 1D sensitive data like eigenfrequencies and probability factors, but also the splitting functions that represent 3D structure. Now, all of these data sets span a period band of roughly 1 to 3,300 seconds, which is a very broad spectrum of data. All of these data sets can be modeled in terms of structure in a planet. And the structure can can have different levels of complexity. It can be either just shear wave velocity, but it can also include P-wave velocity or anisotropy, the topography of the different discontinuities in the Earth, the density in 3D, and currently attenuation in 1D. Please note that all of these heterogeneity can have multiple spatial scales. It's not restricted to having a uniform resolution everywhere. So this is what I mean by full spectrum tomography, because it captures the full period band of data, but also the full spatial band of heterogeneity. Why do we need to do this? Well, if you look at all of these data sets, surface waves, waveforms, travel times, and mode splitting data, red here is the sensitivity with a strong sensitivity, and blue is low sensitivity. If you just use surface wave data, you only have sensitivity from the mohole up to around 150 to 300 kilometers. Inclusion of waveform data can provide you some sensitivity in the mid-mantle and the upper mantle. Travel time data, especially in the way we have set it up, the kind of phases we have in our compilation, provides sensitivity to the lowermost mantle. Mode splitting data is sensitive to the mid-mantle and the transition zone, but it's only by combining all of these data sets that you get more or less even sensitivity throughout the mantle. So this is perhaps the only way to actually circumvent the limitations from one single type of data. Next, I'm going to show you, this was just a sensitivity to VS, or shear velocity structure. I'm going to show you next the sensitivity to different parameters. So bear with me. It's slightly complicated. So each of these rows is a sensitivity for different parameters like P-wave velocity, density, and topography of different discontinuities. You will note that some of these are blue because you cannot constrain P-wave velocities with SS data, SS phases. So that's why it's blue here. But the overall picture is that you need all of these different kinds of data shown in the x-axis to actually constrain features throughout the mantle. And this is especially true because there are trade-offs between the parameters. So if unless you combine all of these data sets, you cannot account for the trade-offs properly. So one aspect that is missed in a lot of analysis is how do we go about predicting data from Earth models? And this is a question of validation because most models use a subset of measurements. And ideally, we should be able to predict the held out data in a robust fashion. So these are just examples of the different kinds of data that is used in the model construction of various models. So this particular study uses all of these data sets. There are other groups that use subsets of these data types. In case of waveforms, it's slightly philosophical in terms of what it means to include waveforms. In here, I mean including actual arrival times of surface waves and body waves, whereas in models like GLAD M15 or SEM-UCB, individual wave packets of surface waves and body waves are included in the waveform inversion themselves. Now, it has not been shown yet is what has not been shown yet is how these blank areas fill out. As in, how well does a model that uses waveforms fit other types of derived data, or vice versa? Like how well does a model created with these derived data fit waveforms? So this is and this is the case for global studies, but also for regional studies. So this is where AVNI kind of tries to find ways to validate Earth models. So let's move on to the the actual construction of models and how we describe them. AVNI is used to create a planet and populate it. The first step is to initialize planetary constants. This is done by configuring geodetic constants that are unique to a planet. For example, the geocentric gravitational constant that might be different between different planets. And this is initialized in the configuration file. As soon as AVNI is imported, it uses the unit definitions of these constants for all the forward modeling. And it uses Earth by default because it's our home planet, but you can define your planet. And the next step is to add shells. So this is defined as a reference 1D class in our setup. These define parameters as a function of depth in terms of radial basis functions. So each of these curves is a basis function for describing variations at depth. On your left is the description for VS structure. The green curves are polynomial functions, and the yellow curves are cubic B-splines. Note that every parameter has a different parameterization in our study, but this can be changed as you like. Once you have created a planet with shells, you can add heterogeneity. And the way to describe that is in terms of perturbations in model parameters with respect to the 1D reference I just talked about. And this can be expressed as a weighted summation of different radial basis functions, BI, and lateral basis functions, SJ. This set of coefficients,Cijk, and the superset of lateral basis functions and radial basis functions represents a realization of a model. Lateral basis functions include examples like spherical splines, spherical harmonics, and pixels. Radial basis functions includes boxcar, constant values, and cubic B-splines. So this is how you incorporate heterogeneity in the mantle. Here are some examples of radial splines and radial splines used in the mantle and in the inner core. And this is the horizontal parameterization with each plus representing a spherical spline. And here is a degree 0 spherical harmonic, which is just an increase in, which just represent a static shift in the value, in the average value of that region. You will note that by combining this horizontal parameterization with the orange splines, you can get the parameterization that was used for describing this model. By adding the blue splines, you can get a different Earth model. By using spherical harmonics with cubic B-splines, you get the kind of inner core model used by Trump in 1993. So the essence here is that you can describe any Earth model using this setup, including regional models. Now, what happens if you're looking at very strong variations in the shallowest parts of the Earth? So, for example, you have basin scale models where velocities change abruptly as a function of distance away from a reservoir. Here is a reservoir scale model, Marmol-C2, which shows, it's a benchmark model which shows strong variations with strong variations laterally. There are also crustal models like Crust 1.0, which have strong variations in MOHO and other structural parameters. Now, the way we incorporate this in our work is to use a grid where each of these colors represent a unique profile. if there were 9 by 9 pixels in this map, so 81 pixel points, and each of them had a unique profile, then it would just be 81 unique profiles. However, we often see that in the Earth, there is contiguity of profiles just because of tectonic effects, or the reservoirs might have similar features with depth. So each of these 81 profiles can actually be represented in this particular example by 3 different profiles, blue, green, and red. And each of these profiles is a reference 1D class that represents values from the surface all the way to the center of the Earth. Now, this profiles class is therefore a superset of 1D reference 1D classes, and represents absolute properties instead of perturbations, like the case was for the earlier classes. And now, once you define a model in terms of these classes, you can evaluate model parameters at arbitrary depths. So this is an example where you read a 3D model, and as long as the reference model is initialized, you can get profiles at any point in the Earth using just 2 lines of code. Now, the reason why we want to look at 1D and 3D models is because for more than a century, people have looked at ball curve structure in terms of 1D models and heterogeneity in terms of 3D models in a distinct fashion. 1D models usually represent average properties with depth in the Earth, and lateral heterogeneity is often captured by 3D models. But there are, I will talk about 2 reasons, but there are other reasons as well. The 2 reasons for treating them together. The first is that the community is moving towards absolute properties. Based on recent experimental and ab initio constraints, we now have thermodynamically self-consistent phase proportions of mineral assemblages and their related properties like BS profiles with depth. We also have complementary constraints from geochemical proxies that report distinct chemical reservoirs, and we need absolute properties because they can actually be used to calibrate the geodynamic models. For example, where the Earth is adiabatic or super adiabatic in the boundary regions. Those are all questions that require absolute properties of the Earth. In seismology, what we have usually done is also treat 1D and 3D data separately. So here are average surface wave velocities as a function of frequency for love waves in green and love waves in red and Rayleigh waves in green. Lower frequencies represent deeper structure, and higher frequencies on your right represent shallower structure. What has typically been assumed is that this is purely a signal of radial anisotropy in the Earth, and lateral heterogeneity is not responsible for this discrepancy between love and Rayleigh waves. But by using AVNI, where we superimpose crust on top of any 1D model, we can show that the phase velocity measurements here, the phase velocity predictions appear like this for 35-second Rayleigh waves. And if you take the average of these maps, you get value like this triangle. And you can populate the dashed curves, which represent the signal from lateral heterogeneity in the crust. And this is a non-linear phenomenon. However, what emerges is that a substantial portion of this signal that is observed in the Earth is actually from lateral heterogeneity. So we cannot actually average out the contributions from lateral heterogeneity while inferring average structure. They need to be looked at together. So this is one of the philosophies of the new radial reference Earth model that we have constructed. I will only talk about the shallowest parts of the mantle and as an example of how things differ from earlier studies. Shown here are variations in anisotropy described as the ratio between horizontally polarized shear waves versus vertically polarized shear waves squared as a function of depth in the mantle. Prem is shown in yellow, and the new model is shown in black. So you'll note that Prem has a monotonically increasing value of anisotropy as we come shallower towards the Moho. However, the peak anisotropy in NRM1D is at a depth of around 150 kilometers. If you compare that to the peak attenuation in NRM1D, it is actually shifted deeper in the mantle, and there are dynamic reasons for this kind of effect that we go into that I can go into later during discussion. What we can also do then is create candidate reference 3D reference Earth models. This is an example constructed from one of the subsets of data showing variations in shear velocities at various depths in the mantle. This is still being constructed, and complexity is being added in the inversions in collaboration with the community. The reason why this is important is because if you look at not only VS variations, but other variations such as density and P-wave velocity, you get signatures of thermochemical heterogeneity in the mantle. So here's an example where we looked at variations of those parameters, and we found different signatures of thermochemical heterogeneity in the mantle, such as median scaling ratios between VS and VP increasing with depth in the mantle, the spread of VS over VP ratios being larger than what you would expect in a thermally driven structure, anti-correlation shown in red between shear velocity and bulk sound velocity in the lowermost 500 to 700 kilometers in the mantle. And the most important effect is that you get anti-correlation between, this is correlation as a function of depth for density variations and velocity variations, and you get an anti-correlation in the lowermost mantle by looking at all of these properties together. So now that we have discussed the tools and how we applied them to data theory and models, let's go back and see how we can incorporate aspects from how you as a stakeholder can be part of this work. One aspect that is very important is that there is a plethora of heterogeneous Earth models, such as those derived from global long period data, the ones derived from global body wave data, and also regional studies. There are differences or discrepancies between these models, and these are primarily due to data and parameterization used in the model. However, the discrepancies are scale dependent. Now, what do I mean by that? If you look at regional models, for example, there is a long wavelength trend that differs between the Western US and the Eastern US that is seen in a model like USSL, but is missing in a body wave type model like DNA 13. However, the smaller scale features are, such as the Yellowstone hotspot, are seen across different models. Same is the case with the Salton Trough and several other tectonic features in the Western US. But the long wavelength trend is something that is missing from the data, from some of these models. So how do we, the question is, can we assimilate consistent patterns in heterogeneity for informing future exploration of the Earth's interior? And what does this all mean in terms of the spectra of heterogeneity? Is the heterogeneity dominated by long wavelength variations, or is it dominated by short wavelength variations? You will note, for example, that the amplitudes of these maps are very different with each, across different models. So the spectra might be different, and our long-held view that the spectra is dominated by long wavelength variations might need to be revisited. So those are the kind of questions that we are aiming for here. And the way we incorporate new constraints from regional work in a global setup is by using wavelets. And this project is also creating a way to assimilate patterns of heterogeneity from regional models into a global framework, whereby you have more or less even resolution throughout the Earth, but finer resolution at continental scales, and even finer resolution at local scales. So as a community, you can get involved, and the way this might work is by you to parameterize and archive models in our formats, store the derived metadata with the guidelines in our papers, use predictions from our reference 1D and 3D models for removing teleseismic contributions while looking at a particular region, and also contributing codes that build on top of our classes. So in conclusion, I have introduced the data theory, model, and community aspects of the 3D reference Earth model project. We have talked about AVNI, which is an analysis and visualization toolkit for plaNetary inferences. This provides APIs, code bases, and web-based applets to query, visualize, and compare data or models. The underlying technique of full spectrum tomography provides robust constraints by providing complementary sensitivities from different data sets. We also demonstrated that lateral heterogeneity and bulk Earth structure, so 3D models versus 1D models, those are a coupled problem due to nonlinear crustal effects. We discussed briefly about the new radial reference Earth model, NREM1D, and a preliminary heterogeneous model, REM3D, whereby we find new features, especially in the boundary regions of the Earth. Through this talk, I would like for you to get involved by using reference data sets, formats, and models, and building on top of AVNI. If you have any questions particular to the AVNI setup, please email us in this email address. And for general queries, please email us here. Thank you so much, and I'm open to any questions you might have.
Wow, thank you so much, Raj. It's really exciting to see the type of science that can be done with AVNI, and also, I don't know if people appreciate the amount of work that's gone into this, the data sets that have been assembled to, make use of these tools, as well as the front end that had to be developed as well to access the data and produce some of the results that you've seen. Open the floor up for questions. Please either raise your hand or type in the chat box, and hopefully we will. There's a long list here, so if we don't see you immediately, just pipe on up. While we're waiting for some questions to come in, I want to remind you that our next webinar will be on February the 17th. Instead of the second Thursday, it'll be the third Thursday, and that will be Takumi Kira from Tohoku University. He'll be talking to us about energy transfer among flow and magnetic fields with different equatorial symmetries during the dipole reversal and a geodynamo simulation. So that should be really very interesting, hopefully illuminating, telling us more about reversals of the geodynamo. Questions? Renee, you have your hand up.
Yeah, hey Raj. I was wondering if you could tell us one of your things about the benefits of the web interface to AVNI? So you mentioned that there are more and more tools that are available online, and I guess the main advantage would be that you can essentially export or the necessary computing power to like do things online. How do you imagine this for the project? So it's still possible to install AVNI locally, but like what kind of computing power would I need to use it locally, or what kind of computing power is available remotely if I want to access the API?
Currently, so that's a good question. So you can install the AVNI package on any computer, and the reason why we have kept a repository in private versus public, so this is the private package and the public package. The reason why we did that is because we wanted the installation to be a very seamless experience and a very small setup in terms of how much resources we were hogging on the local machine. So it is meant to be a very small package. Now, all of these kind of tools can be used locally on any computer. And since a lot of the, there are different implementations. The reasons why why applets are important is because, as you said, like you can delegate a lot of the data storage, archival, and querying options to a server or a bunch of servers in our case, and calculations can also be delegated. So, for example, things like some of these calculations require huge matrix multiplications. So that can be delegated to a GPU server, right? I mean, we don't need not everyone in the community needs to actually buy GPUs when we have the setup to do it in a central facility or a hub, right? So that is the reason why we are in the creation of this software environment. We have kept web-based front end central. So every time we think of some feature, it has to be along the lines of making it possible to serve it as a function to the community. But yeah, it takes more effort, because then if you think about how much allocations you can, how much resources you can allocate on the back end. And as the needs evolve for the community, we can explore other options of what is feasible and what is not.
All right, thanks.
I think you've hinted at that this package will go to a sort of a split release with a public and private repo, and some of that hosted by CIG. Sort of like in the meantime, though, how do people find out more information about model formats, or how to access and use AVNI?
Yeah, so we are creating the web-based setup to actually just, for example, for the reference data sets, like the ones that are already published, we are creating a web portal. So the web portal part of the setup is almost done. So you can obviously play with the data types and play with the reference data sets, and also start using them in your own research. But if somebody wants to if somebody wants to include AVNI in their workflow, they can obviously write to us, and we will be happy to kind of install it for them. But it's not at a stage where we can publicly release it, since the backend part of the service is not up yet. I mean, that's still being worked out, because there are certain authentication issues that we need to figure out, because we can't open it to everyone without accounting for issues like authentication, because that would overload the servers.
Right, so there's both security and sort of internal usage issues as well. Yulian, you have a question?
Yeah, hey Raj. So I was just wondering if you have a plan for when you will release software so that everyone can use it.
I would say my best estimate is sometime in the second half of this year with the manuscript,
Okay.
because we have a manuscript that goes with it. I mean, a lot of it is, so some of the details like data formats are already, they are part of other manuscripts. So for example, this art that I'm just showing on this slide is part of a manuscript that has been published already with a bunch of authors. So like they're coming out, various parts of the idea are coming out in different papers, but in terms of the actual package, my goal is to get it out before the end of the half of this year.